Okay, fine. So in the last lecture, so far what we have discussed is that AM modulated wave consists of a carrier and a lower side frequency or lower side band and a upper side frequency or upper side band. And as we see here, because my message signal is FM, the message is contained in the sidebands only. There is no message contained in the carrier, but you have seen a lot of power is wasted in the carrier. When we talked about the power transmission in AM, 2/3 of the power is wasted in the carrier, and 1/3 is only in the sideband, which are really carrying the information. Also, we have discussed that bandwidth of the AM signal is given by twice of highest modulating frequency. As I said, suppose I have an orchestra playing different instruments at different frequencies, as 5 kHz, 7 kHz, 8 kHz. Then the bandwidth required is the highest of the three message frequencies. That means 8 kHz. So it becomes 2 into 8. That means 16 kHz. And the total power is given by PC1 plus MA square by 2. MA is the modulation index. As we have seen, that lies between 0 and 1. That means 0% and 100%. If it is greater than 1 or 100%, it is a case of overmodulation. Now, moving further, because you are going to do the experiment on AM signal, because when we are going for a laboratory measurement, we have to use a modulating signal, which could be non-periodic, like my speech signal. So there we use what we call, so this is from the lab point of view again, just to make the story complete. It is called a trapezoidal pattern. It is a method. So this is useful. So this is from the lab point of view. But yes, you could be asked questions in the lab or even in the exam. So please note for that. That is also useful for our understanding from the theory point of view. So basically, it is useful when you're modulating. Now we know the modulating signal is nothing. It is the message signal. Like your speech is a non-periodic signal. A speech is not a sinusoidal signal. It is not a. It is varying at various aspects. So it is non-periodic signal. So it is a complex waveform or a complex signal. So what is this in this one? How we do this experiment? It is used for the measurement of various modulation characteristics like modulation index. We can measure the modulation index, percentage of modulation in percent, and the waveform, AM waveform. So all those things we can see in the oscilloscope. How we do this experiment? So here the procedure is like this. There is a carrier signal generator. Carrier is nothing. It is a high frequency. And then we have a low frequency, or what we call the modulating. So basically what we do in the oscilloscope, we use a low frequency signal as a message signal. And then we give these two inputs to an amplitude modulator. Okay. What is that exactly? We'll understand slightly later on how to understand the amplitude modulator. And then we have here is what we call the oscilloscope, which is also called the cathode ray oscilloscope, CRO. Now here we see the pattern, which will be like a trapezoidal pattern. This is a trapezoidal pattern. If we see like this, so here this output is my AM signal, which I get after modulator. And this modulating signal generator also goes to, so one goes here and another signal goes here, which is called a modulating signal input. So this is the typical procedure. Obviously, there is a ground here, there is a ground here, because to make the story complete, and similarly there is a ground here. So this is a typical experiment that you will be doing. You will be generating a high frequency signal, which will be your carrier signal, let's say 100 kilohertz, and you will be generating a low frequency signal using a low frequency signal generator, which we call the message signal, let's say 5 kilohertz. Then you give these two signals to the amplitude modulator and simultaneously to the oscilloscope. Okay. So basically, oscilloscope has two terminals, which I will write in the next slide. So here what we do, modulating signal, this is important from the theory point of view, is applied to the horizontal. So there are two terminals of the oscilloscope. One is the horizontal terminal and another is the vertical terminal. So we apply modulating signal to the horizontal input terminal, and AM wave, finally what is said, we got it, is applied to vertical input terminal of the oscilloscope. Okay, so we got the two things there. Because I want to compare my message signal. If my message signal has a higher amplitude, my modulated signal also must have higher amplitude. So if you see here, one we have applied the AM signal, and other one we have applied in the this one, which I put it is so AM signal we got to the vertical input, and this is the horizontal input, the modulating signal. Okay, so this is how we do go for that. So basically, what will happen if we do so? If we do so, what we see here, your vertical deflection, I think that it will be more clear when you actually do the experiment, but I am writing for you here also. So when you do the next experiment, you just go through these notes also. That is the coming Friday. So it's dependent on the amplitude of modulated signal. Okay, so that is how we do the experiment. So basically we see various patterns, something like this. How we see the patterns, we'll apply various modulation indexes. So how I will see the pattern will look like something like this. If I see the pattern, so let's say there is a oscilloscope, because in the oscilloscope we are seeing time versus voltage. So how I see, so this is let's take the case of a 100% modulation. So if you see the 100% modulation, it will look something like this. That means the maximum is twice and minimum is 0. So your 100% modulation, this is the carrier, which is a high frequency carrier. So you will see in the oscilloscope something like this. So this becomes your V maximum, which you have seen. And here, this is V minimum, which turns out to be 0. That is for the case of a 100% modulation. So if I put the 100% modulation, there is a way to do this thing. So here V minimum becomes 0 and trapezoidal pattern is reduced to a triangular pattern. So it is basically looks like a triangular pattern. So in this case, my trapezoidal pattern is reduced to a triangular pattern. Okay. Because we are seeing it will be given at twice of this one voltage, and here it is 0. This is 0. So this becomes your almost a triangular pattern rather than the trapezoidal pattern. Okay. Now that is the case for a 100% modulation. Now if I have, let's say, 50% modulation, so how it will look? So if I go for the 50% modulation, it will be looking like this. So I have this terminal and then I can mark this as, so V maximum will not be. So in this case, my pattern will look like something like this. If I see the pattern, uh, okay. So here, this is my how my signal will look. Here, the minimum will not go to 0, as you see here. Okay. So here, Hello, anyone of you please, is my slide visible? Am I audible?
Yes, sir.
Yes, sir.
Okay. There was a slight reset. So what we see here, when we do the 50% modulation, you will see a pattern like this, that your V minimum will not go to zero, but it will be something halfway as compared to the V maximum. And then we have another case which we'll also do as part of the experiment, because we have seen the case of over modulation also. So in over modulation, what will happen? So let's take the case of MA equal to 200% or MA is equal to 2. So that means it is over modulation, okay, because your MA is greater than 1. So that is the case of the over modulation. So in this case, what we'll see here, our pattern will look like this. This is something I will draw here, as we have seen. So this is the type of the pattern that you will be seeing. So here it will be your V maximum, and this will be your V minimum. So slightly, I have to redraw this thing. So if you see here, there is another band has come here. Another band has come is there. So this is what we call to lead to splattering, which we have seen that another channel will go into the next channel. So this is the experiment that you will be doing for various modulation index and so on. And we've also seen how we measure the modulation index for such cases. You recall that for the lab purpose, we use this expression VMA is equal to V max minus V minimum over V max plus V minimum. That is for the lab point of view. So you do the various cases of the modulation, 100%, 200%, 0%. That is the most three typical cases, and measure the V max and V minimum, and you can actually find out the actual percentage of the modulation. So this was about the how we go for this one. Now, just to complete the aim part, there is something which we have to discuss also very important. There is also another form of modulation, AM modulation, which is what we call the DSBSC, double side band suppressed carrier, DSBSC. So this is another form of the AM modulation, which is called the AM modulation, double sideband suppressed mode. So basically, what we have learned so far, the AM modulation, it is basically also is called double sideband modulation, because the two sidebands we always get, and double sideband obviously means with carrier. Okay, so AM is a double sideband with the carrier modulation. As we have seen, the expression has got three terms corresponding to the carrier, higher frequency and the lower frequency. Now, what we have seen here in this modulation, the message is contained in the carrier, in the LSP and upper sideband. So what we can do, if I suppress the carrier, because lot of power is wasted in the carrier. Okay, lot of power is wasted in the carrier. We have seen that. That is 2/3 is wasted in carrier, because carrier doesn't carry the information. Carry information. Okay. So if a lot of power is wasted, what we can do, I can't make it zero. I can't make the carrier zero. Okay, because carrier is required. Okay, so but it is taking a lot of power. So can I suppress it? If I suppress it, I can actually get a lot of power advantage. So if I get a lot of power, that power where it will go? It will go to the side frequencies. And side frequencies where it will go? It will actually increase my uh, transmission, AM transmission, or my power efficiency will increase. So basically what we are seeing that in the AM modulation, which I have written in the first slide, there are three expressions, one corresponding to the carrier, another FC minus FM, another FC plus FM. So basically, the two side frequencies contain the complete information, and carrier power is more in the is more than this side power, which is a waste, which is a wastage. So if I remove the carrier, so in the double sideband suppress carrier, what we do, I won't say remove, I will use the word suppress the carrier, because remove doesn't mean then what is the advantage of having the carrier. So we suppress the carrier, but just for your simplicity, suppressing, if somebody doesn't know the meaning, it basically means removal to a certain extent. Okay. So if I remove the carrier signal from the AM wave, okay, we get the double sideband suppressed carrier. Okay. Now it will result in one, increase sideband power level, okay, and hence increased efficiency, power efficiency. Okay. So that is the advantage. We'll get it. Let's see how we are getting the disadvantage. So just see the, if I go for the power in the 1 minute. So I talk about power in the double sideband suppressed carrier signal. So you understood what is double sideband suppressed carrier? That means my power is not there. So what we do? Now they call that, what we have seen, PAM is equal to PC 1 plus MA square by 2. Okay. If I put the best case, which is MA is equal to 1, we have seen that PAM is equal to PC 1 plus 1 square by 2. That means 3 by 2 PC. Okay. Now, but if I have the double sideband suppressed carrier, it is given as PC MA square by 2. Okay. Why? Because there is no carrier. So the first term will not be there. And if I put M equal to 1 here, P double sideband suppressed carrier, it becomes PC 1 square by 2. That means half of PC. So therefore, if I put a P double sideband suppressed carrier over PAM, it also turns out to be 1 by 3. Or P double sideband suppressed carrier is equal to 1 by 3 of PAM. So that is the main advantage we are getting. That is, the power in DSP-SC signal, okay, is only 1/3 of power in AM signal. Obviously, we have done for the case for M equal to 1, and that may be true for other signal. So basically what we'll have here, so what we've seen here, a lot of saving. Almost 1/3 of the power is saved. I'll write clearly here. So almost a lot of the power is saved. So basically, so I can write down here, there is 2/3 power saving in DSP-SC as compared to AM. Okay, so that is the total power saving. But what is the disadvantage? That is the advantage. That is the what we have seen is the advantage of. So this becomes my advantage of AM over DSPSC. Okay. Now what is the disadvantage? Oh, sorry. This is the advantage of DSPSC over AM because I am getting sufficient saving. But what is that disadvantage of DSPSC, double sideband over AM? Because now you have to suppress the carrier. You have to suppress the carrier and you need a complex circuitry. So that is one. But the main disadvantage which I say is that the resultant AM envelope, the envelope that we have got is not a faithful reproduction. As I told you, faithful is a very important word which we use in communication. We say Wi-Fi, wireless fidelity, hi-fi, high frequency fidelity. Earlier we used to say hi-fi. So fidelity means the faithful reproduction of your original signal. Because when I modulate, my signal has been modulated. Then I have to demodulate to recover the signal. How we do the demodulation that we discuss in this later lecture. But we have to recover that signal. And if the recovery should be such that I get the original signal. It should not mean that like what I'm speaking to you now and what you recover at your end is something different. It should be a faithful reproduction. And then we say it is 100% fidelity, good fidelity, and so on. So in this case, what will happen? Your resultant EM envelope that we got is not a faithful representation. That is the biggest advantage of modulating signal. Because because the carrier is not there. So it's not a faithful reproduction or representation of the modulating signal, which is my message signal. And that is, in this case, what is happening? It is simply the sum of lower and upper side frequencies. So this is like what we get in a double sideband suppressed carrier. One advantage, definitely, a lot of power saving. It is almost 2/3 of the power is saved in the DSPSC. 2/3 power saving. That means only 1/3 power. It is 1/3 of the power transmission in the AM signal. And the other thing is also another advantage is the saving in bandwidth. So this is another advantage because you are removing the carrier. So your bandwidth, which was earlier used to be FC minus FM and FC plus MM. So that will not be there because FC is no more there. So it is just simply a lot of saving in the bandwidth. So this is another advantage of the AM signals. So these are the two advantages which I put it here, highlighted here, 1 and 2. And this is the disadvantage. Okay, so lot of saving in power, lot of saving in bandwidth, and another disadvantage could be, as we have seen here, one disadvantage was this. Another is because you have to remove the carrier, you have to use some circuitry also, which becomes complex, and additional circuitry to suppress the carrier. So this is the complex circuitry at the receiver. So it makes your circuit becomes complex at the receiver. So this is another disadvantage. So two advantages and two disadvantages of the double sideband suppressed carrier. Maximum, yes, definitely there is advantage. I am saving the power, but you are not getting the faithful reproduction of my speech signal or the message signal. Okay. So, sorry, not saving in the bandwidth. Sorry, this I put it wrong. I will talk about that. So this is the advantage and disadvantage is there. Now let's talk about the bandwidth of the double sideband suppressed carrier. Bandwidth is the same because still if you see a carrier is still there. Carrier is still there to transmit the frequency. So that is not, so advantage is one that you are getting the 1/3 power saving. Disadvantage, not a faithful reproduction of the message signal, complex circuitry. And let's talk about the bandwidth separately. So what will happen to, just like we talked about the bandwidth power of the DSP signal, the bandwidth of the double sideband suppressed carrier signal. One minute. So how my mathematical representation of my double sideband signal looks. So if I have to representation of double sideband suppressed carrier, so it will look like this: V DSB SC T is equal to, okay, Vm by 2 cos omega C plus omega mt plus cos omega C minus omega mt. That is no carrier term, okay, and where omega is 2 pi f, that we already know. So this becomes my voltage simple representation of my message signal, okay, just like we have for the the double sideband suppressed carrier. So the bandwidth of the double sideband suppressed carrier is B DSB SC is equal to FC plus FM minus FC minus FM. So it is again twice of FM. So it is bandwidth wise, it is the same, where FM is the highest modulating frequency. As I said, if my message signal consists of various message frequencies, or then we take the highest one. So this is becomes my double sideband suppressed carrier. Now, then there is another one, what we call a single sideband suppressed carrier. Because what we have seen here, let me see here. Go to this next slide. So now we'll talk about another modulation, which is what we call a SSB, SC, or simply SSB modulation. This is called the single sideband suppressed carrier, or SSBSC, or simply the single sideband. Now, why it is important? In the previous case, we have seen that the power is contained in the carrier frequency only. Power is carrier in the, message is contained in only the side frequencies, both the side frequencies. Now there are two side frequencies, both are carrying the same information. So why we need two side frequencies? I can have only single side frequency. In the previous case, carrier was not having any message signal, okay, but a lot of power is getting wasted. But the message was contained in the two side frequencies. But when the same message is contained in the two side frequencies, if I suppress one of the sideband also, either lower sideband or upper sideband, I get the same thing. Still, I am getting the same advantage that my message is getting transmitted. So here, as we have understood, can I do a transmission with only single sideband? That means I have suppressed the carrier, I have suppressed one of the bands, still I'm able to do the form. So it is another form of the modulation. So this is the another form of AM modulation in which carrier and one of the sidebands, lower or upper, is suppressed. Is suppressed means are suppressed. Two things are we are suppressing. Because information is contained, same information in both lower and upper sideband. If the same is there, so both the, which means transmission not essential. Okay. So they are the two side frequencies, both are carrying the same signal, FM. Okay. Same information. So if I suppress also one of the sideband, it will also help me in another form of the modulation, which is called a single sideband or the dustband. So in this case, what will happen to my bandwidth and what will happen to my other parameters? So let's talk about the bandwidth. So the bandwidth of the SM signal, what is the bandwidth? It is simply given as, it is simply given by is FM, because there is no FC plus FM, FC minus FM like that. So it is simply SM. Or I could write down this as bandwidth of the sub-sideband is equal to half of the bandwidth of the AM signal or half of the bandwidth of double sideband suppressed carrier, which is simply FM. So this is the main advantage. So this is the one of the that it will require half of the band. So this I would say I would give it as a advantage of SSP, that it reduces, because bandwidth is a very scarce commodity. We have to fight for the bandwidth. Bandwidth by half that of AM or double sideband suppressed carrier. Okay. And when the bandwidth is halved, number of channels can be accommodated and all those things. So this is the bandwidth advantage of a double sideband, single sideband suppressed carrier, and it will have only one frequency. So what is the power? Let's talk about the power of the SSP signal. Move to the next slide. Now, power of SSP signal, because I am taking only one of the frequencies. Okay. It is just a one frequency, one side frequency. So P of singles, it is simply PC MA square by 4. If you recall AM1, we have got two side frequencies which have the power of 1 PC MA square by 4. Okay, so in this case, it is nothing. It is basically half of power in double sideband suppressed carrier. Okay, so this is the power of my SSB signal, straightforward. For 100% modulation or MA is equal to 1, your PSSB is equal to 1 by 4 PC. Okay, straightforward from this expression, or half of power in double sideband suppressed carrier, or 1 by 6 power of because we have seen the power in double sideband was 1/3 of the power of AM. Okay, so this becomes an interesting relation, since we have seen that power of double sideband suppressed carrier is 1 by 3rd of power of AM, as we have just now seen. So this is a good advantage, a very good advantage of the bandwidth. So, but here I will get only the 1/4 of the carrier power or half of the double sideband suppressed carrier or this thing. So let's talk about the advantages of SSP and disadvantages. So first talk about advantages of SSP or SSP-SC. It is one and the same thing. So it is a subset of this thing. 1 over DSP-SC or AM. Okay. So let's see what is the thing. First, reduced bandwidth, as you have seen. How much reduced? That depends from this thing. And basically, what will happen? I have not talked about the noise. Your noise is also reduced because, as you see here, since noise is dependent on bandwidth. Okay, we'll discuss later on when we talk about noise in later lectures. It is basically given as N is equal to KTB. Okay, T is your absolute temperature and K is your Boltzmann constant. Okay, this we'll discuss later on. And N noise is N. And this is Boltzmann constant. We know it is 1.38 into 10 to the power minus 23 joules per Kelvin. Okay. This you must be knowing, but we'll discuss this thing later on. But this is how. So noise is dependent on the bandwidth. So larger the bandwidth, larger the noise. So that will be a challenge. In nowadays we want more bandwidth, but basically it is also more noisy. So here the noise is also reduced great amount, and because of that, these are the two main advantages. And this thing. Another is your power efficiency is increased because your increased, as we have seen here, and so on. But obviously, when we do such thing, now we have to suppress the carrier and also suppress the one of the sideband. So for suppression, we need additional circuitry. So the disadvantage is again complex circuitry, because now you have to suppress two of the things. So basically, you need to suppress the carrier also, which was earlier a disadvantage for the double sideband suppressed carrier. But in addition to that, now you have to suppress one of the side frequencies. So this is what we call the single sideband suppressed carrier. Okay. So if I have to summarize this thing in a simple tabular form, I could, before we finish this topic, so let's put in a summary form. What we have learned, various this thing. So that somebody I could put in this form. So I will talk about parameter. What parameter? Then AM, which is your conventional this one. Then it is also called the double sideband. Okay. Or sometimes we say double sideband full carrier, something like this. Then we have double sideband suppressed carrier, and then we have single sideband or single sideband suppressed carrier. This means full. So there are various ways of talking about this thing. So if I compare for various parameters, let's talk about first is the carrier. carrier suppression. So here there is no carrier suppression. Here it is yes. Here it is yes. Then we have sideband suppression. Here there is no. Here there is no. Here it is yes. One only. One sideband. Okay, you can't suppress both. Okay. And then we talk about the bandwidth required for transmission. Here it is twice of FM. Here also it is twice of FM. Here also it is FM. Okay. And then we talk about power efficiency. It requires minimum. I would say it is moderate. And here it is maximum power efficiency. That means requires less power to transmit my message. Okay. And it requires more power, and which is most of that it is wasted. And then we have what we call the complexity design. It is basically simple and inexpensive, and is complex. It is also a complex design. And when you say complex, means it is more expensive. And then we also have various applications also for that, which, as I said, it is used for the radio broadcasting, AM radio. AM radio, we know that. This is used for typically point-to-point communication. How? We'll later on understand. Just point-to-point communication. Okay. And this is sometimes we use as a long-distance communication. But because it is not a faithful reproduction, we normally follow AM only and double sideband suppressed carrier. So that is the advantage. And AM, we have also seen it is used for the two-way radio communication also, like your citizen band radio and so on. And single sideband is used in the long distance communication, point-to-point communication. Let me see if I could do certain examples for you to make the story complete. So basically, let's do certain example, one or two example based on that. Okay. So this is the story which we have seen. Let me put all in a simple way, another summary, something what we have discussed so far. When I say important, it doesn't mean important is from the examination point of view. So what we have seen, it is just important summary from equation point of view. Okay, so that we could write as in a simple form. VAMT, just for it is written as VC plus VM sine 2 pi FM T sine 2 pi FCT. That is how we started this expression, where VMT is equal to VM sine 2 pi FM T. That is first thing we have learned. Second thing we have learned is MA is equal to VM over VC. And in terms of the modulation index, we could write this as VAMT is equal to VC 1 plus MA sine. Very simple is to understand once you have understood. Nothing great mathematical equations. I put it in a very simple form. Sine 2 pi FCT. So in terms of MA. So this is the expression in terms of MA. And we have seen another expression also, final expression. VAMT is equal to VC sine 2 pi FCT plus MA VC by 2 cos 2 pi FC minus FM. Sorry, I have to put in another plus MA VC by 2 cos 2 pi FC minus FM T back close minus cos 2 pi FC. I have written this expression so many times that if you also write, you will never go wrong. And then we have seen about the bandwidth of the EM signal. It is twice of FM. So this is just the overall summary before we conclude this chapter. And then we have seen total modulation index of complex AM wave is given as MT is equal to MA1 square plus MA2 square if I have, and so on. Also we have seen PAM is equal to PC 1 plus MA square by 2. Here PC is the carrier power. So carrier is the live frequency. And in terms of the current, we have seen IT is equal to IC under root of 1 plus MA square by 2. And today what we have learned is power of double sideband suppressed carrier is PC MA square by 2, and power of single sideband is equal to PC MA square by 4, which is half of power of double sideband suppressed carrier. So these are the three things. This is basically from the power point of view. Okay. So this makes my whole story complete about the AM part. So if I have a modulation signal which is changed from 0 to 1, your power will increase by, suppose I have this one. Okay, so this is all the thing we talk about the AM modulation. Now we start with the new chapter, and that is what we call the angle modulation. That is the frequency and the phase part. So now we move to the new chapter. Let me see if I should start today or, but before I move to that one, any question up to this stage? Any question up to this point, what we have learned? There is one question here. What is right after a complex circuit? Complex circuitry. Okay, so I will clearly, some messages there in the WhatsApp. Somebody is asking me, what is written after this one? Sorry, because I will share my recording also if you let me see how good it comes. Complex circuitry. So complex circuits. And what is the fifth point? Another person has asked 1, 2, 3, 4, 5. Design. How my design is how much complex? And that's why am I peeking also. See, this is the disadvantage of the online communication.
No, sir. After this slide.
After this slide, okay.
Yes.
Fifth point, this
Okay.
bandwidth of the AM signal. Fifth point is bandwidth of the AM signal, BAM. So that is the bandwidth of the AM signal. This is done, you were asking. So these were the two things in the chat messages. I have answered that. Now in next lecture, I'll just give you what we are going to discuss. So basically, we have seen that there are three categories of the modulation. So this we'll discuss in the next lecture. So I put in the next class. But just to give you what we are going to learn now. So we have seen that we have discussed about modulation. So there are two categories. One which is called the linear, and another is the angle modulation. That is the angle part. Linear means here we talked about AM and the amplitude modulation. And angle means angle contains two parts, sine 2 pi FCT plus phi. So that is what we call FM and PM. The frequency modulation and the phase modulation. And because they are part of the same angle, these are related to one another. How? That we have to see. So we normally use FM, never PM, because they are related to one another. So this is the something what we are going to discuss. That means the angle modulation. So in the AM modulation, what you have seen, your amplitude of the carrier is varied in accordance with the amplitude of the message signal. Okay, at every instant. That at some instant my amplitude of the message signal is very high, so my amplitude of the modulated signal also becomes very high. It becomes like a trapezoidal pattern. Okay, it follows that one. But in the angle modulation, my frequency of the carrier signal is varied in accordance with the amplitude only, not frequency. Message signal, we always see the amplitude. But what is the parameter that is varied? That is varied of a carrier parameter. So in this case, my carrier frequency is varied. In the next case, my carrier phase is varied. And carrier frequency and phase are related to one another because both are related to time. Okay, frequency is inversely proportional to time. And time delay is nothing, it is a phase. So they are related to one another. So we have to understand now the basic concepts of the frequency modulation. This AM, as I told you, is used for the radio broadcasting system, AM radio 525 to 1605 kilohertz, which we have seen earlier. And there the transmission is over the large distances because the frequency is small as compared to FM. So now we are going to discuss the FM radio, which is more commonly used nowadays, 88 to 108 megahertz, like your Radio Mirchi 98.3. In our DICT also, we have our own radio, which was started by me only, with your first batch of the BTech students. We started as a small project, and it is a hobby, and we have our own radio also, which is the FM radio. We applied for the frequency, as I told you, to the Wireless Planning Commission. So what happened? Nobody could took the interest in that one from the agency, Wireless Planning Commission. So we tested on our own at one random frequency we have chosen, 107 megahertz, and we found that it is going all within our campus and so on. And in fact, one of the first broadcasts that we did for our own campus is for the convocation speech, where only the final year students are allowed. The graduating students are allowed. No other students. So other students can hear live on the FM radio by tuning to that frequency. How we do that? We have our own FM radio system. We installed on the rooftop, ensure that the power doesn't go beyond our campus. Yes, but you can't stop the power in going. It is not like a boundary. So yes, but nobody gave us the permission because nobody was talking about the radio, community radio that time. So it could not be materialized. So we transmit over the internet nowadays. So our still the radio DICT is getting very popular. where now, but because you are not in the campus, it is not, you are missing that part, but probably very soon we'll be able to see each other. And this FM, our own radio DICT is very popular, especially during the late evenings and so on when the things are getting broadcasted. Uh, we have a radio DICT club under my supervision, like we have electronics hobby center also under my supervision. So that is something you will enjoy. So this is how, but we have to stop it because the permission was not given. Permission was not given because the nobody was taking interest in that time the radio, community radio. But finally, when late Dr. Abdul Kalam, who was our president, and after retirement from president, he went to one college in South. He started his community radio, and when he started his community radio, his application also went there. And then the question was raised in the parliament: how many applications have received? That time they found our application also was lying there. Uh, and they contacted us that they are ready to give the permission to give a frequency. Their team visited us and show that the systems are working, not disturbing beyond DICT. It is a community radio. But they would have given the permission, but they wanted to ensure that you can't broadcast anything without permission. Like I can't broadcast even a song because it is a T series have got the right, or any other music agency have the right, and which was impossible to stop, especially the student community. So no, the student at that time I was also dean students, and no student was ready to take up the responsibility when I talked to my student body government. So we have to give away that frequency allocation idea. But who will see to it? Tomorrow we'll be in trouble otherwise legally. It is not right to broadcast even a song also without necessary permission and rights. So, but still we are doing, but it is we are doing not through the air, but over the internet. Okay, and that is still very popular. So this was a slight story when we talk about the FM radio and all those things, that we have also tried our own community radio. And so in the next lecture, we'll talk about this, a very interesting modulation scheme again. I think I tried my best to write everything for you because yes, many books are available, but I don't know how many of you have the access. You can look for Google's and other thing for your other references or whatever you get access to. But my notes are more than okay. I am writing each and everything. I am also speaking, and I will also share with my PDF file. I will also share my recordings also. Okay, and that's why when you're doing both the things recording also, sometimes I lose this connectivity because of how high bandwidth requirement. But yes, I'm recording each and everything. And now we have got the actual list of the students. So I will make a group and forward these all my lectures, PDF file and MP4 files for you. Okay, so with this, I stop my today's lecture, end the call, stop the recording. Any other message? Nothing else is there. Any other doubt? Otherwise, you can write to me over the email. I will try to answer in my next lecture to all the questions. Sir, can you please show the 8th slide? Yes, there is something has come. Let me go to the 8th slide. This is slide 14, 13, 12, 11, 8. Yes. So this is the 8th slide. Yes, what is the question for you? So basically here I say the advantage of this double sideband is that your power saved is 2/3 of the power. Okay, as we have seen in the previous slide, it is almost 1/3 of the power of the AM. Okay. So power in DSP signal is only 1/3 of the power in AM signal for MA equal to 1. Okay. That means 2/3 of the power saving you are getting here. And disadvantage is that you will not get a faithful reproduction because now your carrier is missing. It is simply the sum of the lower and the, I will write it clearly for you. There is upper side frequency. So it is not a faithful reproduction. Otherwise, so, and also we need complex circuitry. Again, I think that is a disadvantage. Circuit. Okay. So these are the some of the disadvantage. Is anything else you want to ask from this slide? Can you please also show the points where you wrote for the trapezoidal pattern? And another question has come. Very nice. I love questions being asked. Trapezoidal pattern, okay, it was in the start only. Okay, fine. This is for the lab purpose. As we have seen, for the lab purpose, we measure the modulation index in terms of MA is equal to Vmax minus V minimum over Vmax plus V minimum. Yes, this is the one, trapezoidal pattern. So here, what we do here, we have an amplitude modulator, and there we send the two frequencies, one carrier frequency, which is a high frequency, another is low frequency, which is, let's say, is my message frequency or speech frequency. And then through this amplitude modulator, I get an AM wave, which we apply to the vertical input of the oscilloscope. And the modulating signal generator of the also gives my message signal directly to the oscilloscope. That is the horizontal pattern. Okay. Once we go for this, we'll get something like a trapezoidal pattern. This I already told you. So we get a trapezoidal pattern like this. So when you'll be doing this, you'll be applying various type of modulation indices and so on. And this is the case for the 100% modulation, that you will get 0 minimum. Sorry, it got rubbed. Okay. Then 50% modulation, that means V minimum is almost half of the V maximum. And then you try for one case of over modulation. So that's like another band has been created. So like splattering has done. Okay. And in this case, we normally measure the modulation index by using this expression Vmax minus V minimum over Vmax plus V minimum. So this is the experiment you'll be doing in this Friday, coming Friday, and that will help you. So trapezoidal pattern method we use for actual measurement in the labs and other thing for seeing the complex signal like my speech signal and so on. So it is like a trapezoidal pattern, and it reduces to a triangular pattern when my modulation index is 1 or 100%. Okay, is that clear? Okay, thank you, Pinak Trivedi. Okay, fine. So I stop it here and share the slide for you. Just end this call. I leave this call, stop the recording, and so on. Mm-hmm.